This is the Feynman path integral, also known as a functional integral. And if you were to ask 100 physicists, Family Feud style, to name the most essential mathematical tools in modern physics, the path integral would come out at the top of the list. Because it's key to our understanding of everything from quantum mechanics to statistical mechanics to the standard model of particle physics. And in this video, I'm going to show you how the path integral is defined, why it's so important, and how to actually compute it in an explicit example. Because a path integral is not like any integral you've seen before in, say, your intro calculus classes. With an ordinary integral like this, we look at a function f of t that assigns a number to each point t along a line. Then the integral of the function over some range computes the area under the curve in that region. And to work it out, we just imagine slicing the region up into lots of skinny rectangles, each one of width dt and height f of t. The area of a given rectangle is then the product dt times f of t. And by summing up those contributions from all the rectangles, and moreover letting their widths shrink down to be infinitesimally small, we obtain the total area under the curve, the integral of f. But that's for an ordinary integral. A path integral is a different and much more complicated beast. Instead of summing over a range of points on a line, we do a sum over every possible path connecting a given starting point and ending point. To each path, x of t, we assign a number, phi, a complex number, in fact, which you can think of as an arrow in the complex plane. Each path gets its own arrow, where again, we need to consider every possible trajectory connecting these 2 points. By adding up those arrows for every possible path, multiplied by a corresponding measure factor, dx, we obtain the path integral of phi. And if doing a sum over an infinite set of paths sounds complicated, I won't lie to you, it definitely is. But to begin to understand why this thing is so important for physics, imagine we have a quantum particle like an electron that starts out at this position xi at an initial time ti. Then, after waiting a little while, at a final time tf, we look for it at some other point, xf. Feynman showed that instead of moving along a single classical trajectory that something like a baseball would have followed, for an electron, we need to consider every possible trajectory that the particle could conceivably follow. And only after summing over all those trajectories, in other words, by computing the path integral, can we obtain the quantum mechanical probability that we'll find the particle at this final point when we go to measure it. More precisely, the probability is proportional to the square of the path integral. This, schematically, is Feynman's path integral approach to quantum mechanics. And it's kind of a wild idea when you stop to really think about it, both physically and mathematically. Because again, it says that a quantum mechanical particle doesn't follow a single path like we're used to in classical mechanics, like, say, the parabolic arc of a baseball flying through the air. Instead, the particle does a kind of statistical average of every possible trajectory between the endpoints, including paths that zigzag to the moon and back before finally winding up at the ending position where we observe it. That's what the path integral computes. And in this video, I'm going to show you how to unpack what the heck it means. And in doing so, we'll discover the particle's quantum mechanical wave function without ever even writing down the central equation of quantum mechanics, the Schrödinger equation. This is actually the third in a series of videos that I've posted about the path integral and Feynman's approach to quantum mechanics. I'll begin here by taking a couple of minutes to review the main results we discovered before, and then we'll see how to put it all into practice by working through an actual path integral calculation. And as usual, you can get the notes that go along with this video for free at the link in the description to follow along with all the nitty-gritty details when you're ready. The physics of quantum objects, that is, of very tiny things like electrons, is very different from what we're used to up here in our more familiar classical world. Like I just mentioned, quantum particles don't move along the well-defined trajectories that we see for everyday objects like baseballs. A baseball, if you throw it up in the air, will travel along a simple trajectory, x of t, where in this picture, I'm graphing time on the horizontal axis and the particle's position on the vertical axis, its height above the ground in this case. And the result is a parabola that connects whatever initial height xi, where the ball started at the initial time ti, to the final height xf, where we find it at any later time tf. That's the classical trajectory. And it's easy enough to work out by solving F equals ma with the force of gravity pulling down on the ball. Importantly, if we know what the ball was doing at the initial time ti, we can predict precisely where we'll find it at any later time tf. But quantum mechanics turns all that on its head. Even if we know exactly what a quantum particle was doing at the initial time, all we can predict for when we go to measure it again later on is the probability that we'll find it at some position. The particle might wind up there, or we might find it somewhere else. And that means that in between, the particle doesn't follow a unique trajectory like the baseball did. Instead, Feynman showed, and we discovered in the previous videos, that the particle averages over every possible trajectory connecting those endpoints. And we saw how all that comes about by exploring the famous double slit experiment, where we chuck quantum particles at a wall with 2 tiny holes cut into it, and we see what comes out on the other side. If a quantum particle moved along a single trajectory, like a baseball, we could say for certain whether the particle passes through the left slit or the right one. And then we'd expect to find that most of the particles that make it through wind up somewhere in the middle, like this, distributed with a broad bump around the center of the backstop. But that's not what happens. Instead, we wind up with a distribution that looks something like this. It's called an interference pattern, with peaks where we find lots of particles clustered together, separated by valleys where next to none arrive at all. Somehow, each particle that travels through the barrier probes both slits at once and interferes with itself. And as mind-bending as that fact may be, this simple experiment already leads to the basic idea of the path integral. Because if we imagine drilling a third hole in the barrier, we'd have to include trajectories that pass through that hole as well. And the same goes if we drill a fourth hole or a fifth hole, and so on. Taking this idea to the extreme, Feynman imagined filling the entire region with barriers and drilling lots of tiny holes through each of them. Then we'd need to consider every possible route the particle could follow, bouncing from one hole to the next on its way across the gap. And eventually, we can imagine drilling so many holes that the barriers themselves effectively disappear. And we're led to the conclusion that the particle probes every possible path in getting from this initial point to whatever final point where we observe it at the detector. And we need to sum over all of them. That's the physical motivation behind Feynman's path integral formulation of quantum mechanics. To determine the probability that the particle will be found at some final position, xf, we need to sum over every possible trajectory that it could have taken to get there. But what exactly are we supposed to be adding up here in this sum? Well, in the last video, I explained that to each path we assign a certain complex number, e to the I times s over h bar, where h bar is the fundamental constant of quantum mechanics, called Planck's constant, and s is a number called the action that we can compute for any given path. It's defined by taking the kinetic energy of the particle at any moment, minus the potential energy, and then integrating that difference over time along the trajectory. So we pick any path x of t, connecting the initial point to the final point. Then we perform this ordinary integral of the kinetic energy minus the potential energy along that path, and the result is a real number that we can assign to this trajectory, its action. Different paths will have different values for the action, and therefore each term in this sum will contribute with a different weight, e to the I times s over h bar, which is a complex number that you can picture as an arrow in the complex plane pointing at the angle s over h bar. One path might contribute an arrow like this, while another path points off in some other direction like this. And according to Feynman, we need to add up all these arrows for all the possible paths in order to predict where we'll find the particle when we go to measure it again. That's all very schematic though. Now let's dig into the details of how we'd actually go about defining this sum, what it computes for us, and how to evaluate it in a concrete example. First of all, let me state again precisely what it is that we want to calculate here. We've got this quantum particle, which is starting out at position xi at an initial time ti. And the question is, if we wait a little while and measure its position again later on at time tf, what's the probability that we'll find the particle at some other point xf? And here again is the answer, according to Feynman. As before, we consider every possible trajectory, x of t, that connects these initial and final points. For each path, we evaluate its action s. And from there, we write down the corresponding complex phase that it contributes. Then we do the same thing for all the other paths, and we add up the complex phases that we get from each of them, along with an overall factor a that we'll work out later. The result is called the amplitude for the particle to propagate from point I to point F. And I'll write it like this, as kFi. It's not quite the probability that we're looking for yet. After all, k here is a complex number. But in general in quantum mechanics, to go from an amplitude to a probability, we just need to take the absolute value and square it, so that the probability we want is proportional to the absolute value of k squared. Finally, what we're really looking for here is the probability that we'll find the particle within a little window around this point. And so the last thing we need to do is multiply it by that tiny width, dxf. This is the central result of the path integral formulation of quantum mechanics. And of course, the hard part here is how to actually evaluate this amplitude k by summing over all the possible paths between our initial and final points. And that's what we're going to tackle now. First of all, the set of all these paths isn't a discrete list. And so we're not actually doing a discrete sum here. Instead, it's a path integral. And so we write it like this, which stands for the integral of e to the I times s over h bar over the space of all paths from point I to point F. But if there's an infinite continuum of paths that go between our 2 points, how the heck are we supposed to do a sum over all of them? Well, we can follow a very similar strategy to the way you learned to define an ordinary integral in your first calculus class. With an ordinary integral, we basically want to add up the values of a function f of t for each point t in a given range on a line. But instead of jumping straight to summing over this continuum of points, the way we define this thing is by breaking it up into a series of discrete steps. So let's say we divide it up into n steps, from ti to t1, from t1 to t2, and on all the way up to tn-1. And finally, our last point, tf. In fact, let me rename the initial point here to t0 and the final point to tn to really make that pattern clear. The total width here is tn minus t0. And so the width of each of these smaller intervals is that total divided by n. And I'll abbreviate that as delta t. And now that we have a discrete list of points instead of a continuum, the problem becomes much simpler. For each point, we just write down the value of the function, the height in other words, and we multiply it by the tiny width, delta t. That gives us the area of a rectangle under the curve at that point. So this first one gives us an area of delta t times f of t0. The next one has area delta t times f of t1, and so on for all the other rectangles all the way up to the last one, delta t times f of t n-1. And so we can write the total area of the rectangles as delta t times each value of f, summed over all the individual steps. And that gives us a discrete approximation to the actual area under the curve. But now, by letting the number of steps n get really big, the rectangles get skinnier and skinnier, until finally, in the limit that n goes to infinity, we obtain the exact area under the curve. This limiting expression is what we mean when we write down the definite integral of a function, where the notation is meant to indicate that we're summing over the continuum of points between ti and tf, while letting the width delta t shrink down to the infinitesimally small measure dt. Okay, hopefully all that is mostly familiar, because now we're going to apply a very similar procedure to understand the path integral. So now let's return to the amplitude k, where we want to integrate this quantity phi over all the trajectories that connect point I to point F. Phi here is called a functional, by the way, as opposed to an ordinary function. It takes in a whole curve as its input and assigns a number to it, compared with an ordinary function that simply takes in one number and returns another. It's common to write functionals using square brackets like this, and the whole path integral is therefore also known as a functional integral. But once again, instead of jumping straight to trying to sum over the continuum of all possible paths, let's start by turning it into a discrete problem. So here's some trajectory x of t. Just like before, we can take this time interval and break it up into n discrete steps, from ti to t1, from t1 to t2, and so on, ending with tn-1 and the final time tf. Then, for each of these times, the trajectory assigns a corresponding point in space, x1, x2, and so on, all the way up to xn minus 1. And by joining those points up with straight line segments, we can make a zigzag approximation to our original path. And the same goes for any other path we might draw. We just shift our points up or down to make a zigzag version of each new curve. And in that way, we can make a discrete approximation to any path that we like. And so, if we want to sum over all those possible trajectories, we just need to sum over all the possible values of x1, all the possible values of x2, and so on, all the way up to xn minus 1. In other words, we're going to integrate over the entire range of potential values for x1, from minus infinity all the way down to plus infinity all the way up. And likewise, we'll integrate over all the possible values of x2 and x3 and on and on and on until we get to xn minus 1. That's how we'll construct the sum over all paths, by integrating over all the possible positions of the intermediate points. And like I mentioned earlier, I'm also going to include an overall constant a here, which we'll see will be important for actually getting a sensible answer out when we take the limit. Because, just like before, the last thing we want to do here is to take the limit as n goes to infinity, so that the time intervals between our steps become infinitesimally small, and we're able to account for every possible path between the endpoints. And this, at last, is how we'll define the path integral of our functional phi. But still, all this must still sound very formal. So let's make it totally concrete by working out an explicit example. The path integral for a free quantum mechanical particle. So here again is our quantum particle. Remember, it started out at position xi at the initial time ti, and our job is to figure out the probability of finding it at some other point xf at a later time tf. According to Feynman, the amplitude for the particle to propagate from point I to point f is given by the path integral of e to the I times the action s divided by Planck's constant h bar. And if we can work out this integral, we'll have answered our question, because the probability is then simply determined by the modulus of k squared. So let's roll up our sleeves now and see if we can work this thing out. And again, to keep things as simple as possible, let's assume that we're dealing with a free particle, meaning that it doesn't have any forces like gravity or electromagnetism acting on it. If it were a classical particle, then the solution to F equals ma with the force equal to 0 would just be a straight line. But as we've discussed, in quantum mechanics, things are not quite that simple. Instead, we need to sum over all paths weighted by e to the I times s over h bar, where the action s, remember, is defined by taking the kinetic energy, 1/2 mv squared, minus the potential energy u, and integrating that difference over time along the path. For a free particle, though, the potential energy is 0, so we can throw this second term away. And so, what we need to do to evaluate this path integral is to write down the value of the action s for each possible trajectory, raise it to e to the I times s over h bar, and finally sum over all the paths. So here again is some arbitrary path. Like we just discussed, the way we're going to handle it is by breaking it up into n discrete steps and approximating the curve as a zigzag. Each piece of the trajectory is then just a straight line. And so it's actually not hard at all to write down the action for each segment and then add it all up to get the total. Take this first segment, say. The total time interval here is tf minus ti. And the length of each of these smaller intervals is that total divided by n. And I'll call that delta t again, like we did before. So in this first little time interval, delta t, the particle starts at position xi and moves up to position x1. And since the trajectory is a straight line, the speed dx by dt is constant. It's just the change in the position over the change in time. And constant speed means that the kinetic energy, 1/2 mv squared, is constant too. And so when we integrate that constant over the little time interval to get the action, we just get the length of time, delta t, times the constant value of the kinetic energy. And that gives us the action for this first line segment. Now, we just need to do the same thing for all the other line segments, and then we add them all up to get the total action for the whole trajectory. They all take the same form though. The second one goes from x1 to x2, and so it contributes x2 minus x1 squared. And likewise, we add on and on from there, all the way up to the last segment, with xf minus xn minus 1 squared. That gives us the total action for our discretized path. And raising it to e to the I times s over h bar, we obtain the total weight for the path integral. Finally then, we're ready to take this weight and plug it in to our limiting definition of the path integral, which remember is given by integrating over all the intermediate values of x. Now I know this is a little scary looking, but it's actually nowhere near as bad as it looks. Because at this point, we've managed to boil the whole path integral down to a handful of ordinary integrals over x1, x2, and so on. And each of those ordinary integrals is something that we can evaluate exactly. They're called Gaussian integrals, and there's a famous formula for them that you might have run into before. So basically, we just need to apply that formula here, n minus 1 times over, for each of these integrals over x1, x2, and so on. That's not terribly exciting, so for now, I'll just tell you what it comes out to, and I'll show you how to get there step by step in the notes for when you're ready to tackle the details. So, after we do these ordinary integrals, we wind up with this expression involving the positions and times and m and h bar and so on. It looks a little complicated, but the main thing I want you to notice right now is that the only thing that depends on n here is this factor, which is raised to the nth power. The rest has nothing to do with n at all. And therefore, in order for the limit where we take the number of steps to infinity to make sense, this factor in front has got to be canceled out. And that tells us that this overall constant a had better be the inverse of that factor. That way, all the n's disappear, and at long last, we're left with the exact result for the free particle path integral. This is the quantum mechanical amplitude k for a free particle to propagate from position xi to xf. Okay, but now of course we should discuss what the heck this expression actually means physically, because there's an important general lesson about quantum mechanics lurking in this formula. Remember that our original question here was to determine the probability of finding the particle at position xf within a little window of width dxf. And to go from the amplitude to the probability, we just need to take the absolute value squared times that little width. In other words, the square of k tells us the probability density of finding the particle at any given point. So what do we get when we take the modulus squared of our result for k? Well, the second factor here is of the form e to the I times something. So it has absolute value 1. So that doesn't contribute anything to the probability, and all that remains is this first factor, whose absolute value squared is m over 2 pi h bar tf minus ti. This, at last, is the probability density for finding the particle at position xf, given that it started out at position xi. There's something really surprising about it, though. The answer doesn't actually depend on the position at all. In other words, if we plot this probability as a function of the final position, we just get a constant horizontal line. And that means that the particle apparently has an equal chance of being found anywhere in space. But how the heck can that be? The reason comes down to another fundamental principle of quantum mechanics, the Heisenberg uncertainty principle, which says that the more precisely we try to pin down the position of a particle in space, the wider the range of velocities it can have. And since we assumed here that the particle starts off at exactly position xi, its initial velocity could be absolutely anything. And therefore, the particle can shoot off from that initial position to any other point in space when we go to measure it again later. Of course, in reality, we can't know the initial position of the particle exactly. And so a more realistic initial setup with a window for the starting location would give us a smaller range of possible final positions and a normalizable probability distribution. Now, there's a lot more I'd like to tell you about path integrals, including the fact that the measure, capital Dx, isn't actually well defined. But I don't want this video to become crazy long, so I'll explain a bit more about some of those details in the notes. For now, let me wrap up by coming back to something I mentioned at the beginning, the connection between Feynman's path integral approach to quantum mechanics and Schrödinger's formulation in terms of wave functions, because these are not two separate theories. They're just two different perspectives on the same underlying physics. In fact, the amplitude k that we've computed with the path integral is the wave function for a free particle that started out at position xi. To simplify a little, let's suppose that the particle starts at the origin at time 0. Then we can set xi and ti to 0. And we also don't really need the final f subscripts anymore, so I'll get rid of those as well. Then this is the wave function for this particle after we release it from the origin. And in particular, it had better satisfy the Schrödinger equation, which says that taking the time derivative of psi is the same as taking two derivatives with respect to x, up to some constant factors. So let's see if it works. We just need to evaluate these two derivatives of our function psi. I'll let you grab a piece of paper and compute those for yourself. You should get minus 1 over 2t times 1 plus im over h bar t x squared, all times psi, and a similar expression for the derivative with respect to x, but with a factor of im over h bar t out front. Then, lo and behold, when we simplify those factors out front, we wind up with the exact same thing on either side. And so, this wave function does in fact satisfy the Schrödinger equation, as promised. But using the path integral, we were able to derive it without ever even talking about the Schrödinger equation, and just considering regular old particle trajectories, albeit an infinite number of them. Again, remember that you can get the notes for free at the link in the description. That's also where you can sign up for my email newsletter to get extra bite-sized physics lessons delivered to your inbox. Thanks to all my supporters on Patreon for helping to make this video possible. You can join too at the link up in the corner if you'd like to see more videos like this one in the future. And of course, you should subscribe to the channel, hit the like button, and leave a comment down below if you found this video helpful. Thank you so much for watching, and I'll see you back here soon for another physics lesson.